Welcome to week 10. Woo! We made it. Sort of. We got here. Anyway, I am just switching my screen share. Oh my gosh. Oh, there it is. Okay. So today I titled this one Wrapping Up Loose Ends and More Content Than We'll Get to. I really overestimated how much we would get through in this class. So there are some topics that we didn't really cover in as much depth as I would have thought. And we didn't get to several topics that I thought we might be able to get to. So if you're interested, the things I was thinking we would do more of, we're going to talk about missing data today, but I thought we'd go quite a bit deeper than we'll have time to today. And I also really thought we would talk about piecewise models. I thought that was like a for sure something we would talk about, but we're not going to get to that today either. And the reason is because I chose to instead focus on non-nested models because I think that's more common, although piecewise models are really helpful. And then the last part is splines and things like different ways of handling nonlinearity. So if you're interested in those topics, I'd recommend exploring them. And even after the term is over, you can always feel free to reach out to me, and we can chat about what you're doing. And I'd be happy to have conversations with you. Okay. So here's the agenda for today. We're going to review homework 3. And then we're going to, instead of doing equation practice, we're going to do research questions to models practice. Okay, so I will have some research questions and then ask you to write a model for it. This is a little bit more difficult because there's not always like one correct way to do things. Sometimes there are, but sometimes there are not. Okay, sometimes there's multiple ways. So I'll kind of walk you through that as best I can. Then I want to sort of finish up on what we were doing last time with Bayes, specifically on the sort of multiple comparison stuff. So there's quite a bit of slides there, but I'm going to cover that really quick until we get to the parts that we didn't cover last time. But most of that is sort of just like refreshing your memory on where we were. Then we will talk about missing data. I'm going to talk about multiple imputation in R, and then I'm going to talk about a different way of doing imputation specifically with Bayes, using the posterior to impute your data, okay? And then we'll jump to cross-classified models. I think we'll actually probably be able to get through most of that. And we'll have a brief little discussion about multiple membership models, which are sort of a different way of thinking about cross-classification. At the very end, I'm guessing we will not have time for this, but I did include some slides on fitting a one parameter logistic IRT model through a mixed effects regression sort of framework. Okay, I just think that's kind of a neat thing, and so I basically show you how to do it, and then I show you how the results are the same if you use a package that's meant to fit an IRT model. But the thing that I think is neat about it is that once you conceptualize it within a multi-level framework, then you can, of course, add additional predictors and do all sorts of different things to extend the model pretty easily. Okay, so that's kind of neat. Any questions on that? Okay, so now we're going to move on to review homework 3, and I actually need to get R going, so give me just a second here. Homework 3 is here. So as I mentioned in class, and I hope the directions were clear enough, the only real part that you were supposed to do was this part, where I do think it got a little bit confusing, and I think I saw quite a few people doing additional work, and at first I thought that was just because you wanted to do the additional work, but then after some conversations, it sounds like some people were confused. This is the only part I was asking you to do, so just that. And so then there's my answer for that, and we'll go over that in a second. Everything that was from the rest on is just additional practice. Okay, so if you wanted to do that stuff, you could. But I think where it maybe got a little confusing is I have 1, 2, 3 research questions in the rest. And so when I'm saying research question 1, I'm referring to research question 1 in the rest, not research question 1 as in this one up here. Okay, so so I probably should have actually labeled these like RQ1, but I didn't realize that was going to be confusing until after the fact. Okay, so I'll actually do that now, even though it probably doesn't matter because I'm probably never going to teach this class again, but what else? So that was what I was thinking. Okay, so let's go back here and look at this one. Okay, so the question is, we're dealing with this Thai education data set. All right, and the question is, does the relation between students' coded sex and the likelihood of repeating a grade depend upon the mean SES at the school level? Okay, so basically what we're saying is we have some relation between sex and the likelihood of repeating a grade that we're expecting to be there because of past research or whatever. Okay, or maybe we've already done those analyses and we just know that that's going to be the case. So then the question is, does that difference, whatever the difference is between students who are coded male and female, does that difference change with the mean SES of the school? Okay, so if it's a really high SES school, is that relation bigger or smaller, right? And then vice versa, if it's a really low SES school, is that difference bigger or smaller? Okay, so an interaction would be, right, in a very low SES school, you have a really big difference, and in a really high SES school, you have a very small difference or no difference, or maybe a reversal in the effect. Okay, any of those would be interactions. And that's what this question is about. Technically, it's a cross-level interaction because mean SES is a school-level variable, and it's predicting a student-level variable, sex. Okay. However, when we're actually modeling it, it doesn't really matter if it's cross-level or not. Okay, the cross-level part of it is really the nature of the data, not like you can think of it in terms of research questions, right? But it actually doesn't matter in terms of how it's estimated. And so this is again where it's better, I think, to have a really strong understanding of just regression generally and just sort of think of it like that. And then when you're fitting a multi-level model, you're taking some parameters and saying, okay, this parameter I'm going to assume is generated from a distribution. So it's not going to just be a parameter, it's going to be a distribution of parameters where I'm going to get basically a different parameter for every student or for every school or for every whatever. Okay. So I said you must use Bayesian estimation. So that means you're using BRMS, and provide evidence to justify your conclusion. So that's basically interpret it. So answer this and then give me an answer, right? And then provide some evidence to justify that answer. Okay, and then I said make sure to also account for the between school variability in the baseline log odds of a student repeating a school. So the baseline log odds just means the intercept. Okay, so essentially we're going to fit a model where we look at this relation, right? Sex predicting likelihood of repeating, mean SES predicting likelihood of repeating, and their interaction predicting likelihood of repeating. And then we're going to allow the intercept to randomly vary across schools. Okay, that's the model we're going to fit. So first we're going to, I need to load my packages. So let me do that. Okay, and then this is what the data looks like. All right, now I need to transform my outcome. And we could actually just change this to be, so repeated grade, we could just change it to be a factor. And we would probably want to set yes as we'd probably want to set no as the reference group, right? So we'd be modeling yes, they're repeating. Alternatively, you can just do it like this. So I just created a new variable, which I called out, the outcome. And I'm saying if repeated grade is defined as yes, then it's going to be 1, otherwise it's going to be 0. So anytime you're fitting a binomial model, your outcome either needs to be a factor or it needs to be 0, 1. Okay, so I did that. And now we can look at TD again, and it looks like this now, right? Here's a bunch of kids who did not repeat, all right? And then we're gonna fit our model. So I already loaded BRMS, I think. Yes, I did. There's broom.mixed and BRMS there and tidy bays as well, okay? So I'm calling this M3 because this is, if you did all of them in order, this is the most complicated model. So it's sort of, if you're going in order, this is M3, but it's M1 really because it's the first one we're fitting because we're skipping all of the previous stuff. So out is my outcome. That's going to be modeled by sex times MSESC. So MSESC is the mean SES of the school, but it's centered, okay? And so, and then I'm going to allow the intercept to randomly vary by school IDs. So again, this is the same thing as that, okay? Those are equivalent, okay? Data is going to be TD. Family is going to be Bernoulli because I'm using BRMS. If I was using LME4, this would be binomial. Link is Logit. Cores is for backend command stand. This is just stuff to make it go a little faster. And then I also have this control list adapt delta equals 0.99. If you look at those warnings, the warning guidance that I sent a link to last time for STAN programs, one of the things it talks about is divergent warnings, okay, or divergent steps. And those are actually pretty problematic. I think you only run into one divergent step here, so it's probably not a big deal. But if you run into more than that, then it is a big deal. So by default, adapt delta is 0.9. You can set it to 0.99, and that changes the way the algorithm runs. It makes it slower, but it will avoid those divergent steps, okay? So that's what I did. We can go ahead and fit this. It will take a little bit of time, but it shouldn't take too terribly long. Yep, Chris?
So I think I emailed you back and forth about this a couple times, but so we're not using sex as a random effect. I kind of thought we were doing a random slope for sex based on this model.
No, so if we look back at the research question, it's just asking if the relation between students' coded sex, so that relation, coded sex and likelihood of repeating, depends on mean SES. Okay, so it's not saying, does it randomly vary across schools or does it depend on school, right? If we wanted to say, does the likelihood of sex depend on school, likelihood of repeating based on sex depend on school, then that would be a random effect. But in this case, we're saying basically there's one slope or one difference between males and females, people who are coded male and female in this data set for likelihood of repeating. And whatever that is, we're going to assume it's fixed across schools. And then there's one slope for mean SES, and we're going to assume that's fixed across schools. And we actually can't allow that one to randomly vary because it's at the school level. And then we're going to have that same thing, mean SES, be a predictor of that sex slope, right? So we still only have one slope, but we're saying it's going to, the magnitude of that difference is going to depend on the mean SES of the school.
Okay, the way that the question 2 coming after question 1 and the rest part made me really question that logic so much, but okay, I'll think about that a bit more.
Yeah, it's an interaction just like any other interaction, right? And so there's really no difference there. It's just, you're just saying, does the difference between people who are coded male and female differ across schools? And so that would be randomly varying. Does it differ by the mean SES of the school, right? And so it is confusing, I think, in part because it's a cross-level interaction. And so the mean SES at the school sort of says, well, it is randomly varying across school because the value of the mean SES is changing in each school. But still, that relation is like that interaction is assumed constant across all schools. So we can predict, it's just fixed effects for those things. They're just adding together.
Gotcha. Yeah, I think the research question to formula practice today will help with with this.
Yeah. Okay, so after that, it says all 4 chains finished successfully. It took about a minute, so that's cool. I can do summary on M3. Pull this up a little bit, and you can see we have, pull this over. So this is all still, let me run this. Let me get rid of this. Okay, so we have, these are basically our fixed effects down here. But, you know, in a Bayes sort of framework, fixed effect is kind of like a weird term because these are all distributions of parameters themselves. But they are the distribution of the mean effects, basically. Okay, so this is our baseline log odds, and then this is the standard deviation of those baseline log odds across schools. Then we're saying students who are coded girl are on average have a reduced likelihood, right? And then as the mean SES of the school goes up, the likelihood of being retained goes down. And then the interaction is also negative, okay? So what does all that mean? Well, let's sort of walk through it, okay? First, one of the things I did in this case, and there's multiple ways to do this, but I showed you this last time, is we can use get parameters from the insight package, okay? And that will just basically pull the posterior distribution for us. So now I can say head posterior, but it'll only do it for those like fixed effects, those mean effects, okay? So here's the posterior for the intercept, for sex girl, for mean SES, and for the interaction between them, all right? So what I'm going to do now is just look at that interaction, which is here, okay? And I'm just going to look at the density of it. So I'm basically looking at the distribution of the posterior distribution, and I'm putting a vertical line at 0 just so I have sort of a reference, right? And again, if this distribution is like centered on 0, then I would have pretty good evidence that, you know, the most likely effect that we're estimating here is 0 effect, right? But the extent to which it's different from 0 gives us more evidence that it might not be 0, okay? So I do that and we get something that looks like this, okay? And so again, if we were in the world of frequentist land, we would say, well, this crosses 0. There's probably, you know, if we were to look at a 95% confidence interval around this mean, it would probably cross 0. So then we'll just conclude, oh, there's no difference. This is not meaningful. But generally, in the Bayes world, that is not how we interpret things. It's much less take and throw away. All right, it's much more about just discussing the probability of things. Okay, so one thing we can do. This is just looking at. I don't know why I'm doing this exactly. This is looking at the basically a 95% confidence interval for girls as opposed to boys. So that difference is, so right, the intercept would represent boys, and then the intercept plus this coefficient would represent girls. So I can kind of look at both of those. I'm going to pull this on there. So if I get rid of this, that would be for boys, right? So you can kind of see the difference in the log odds between those two groups. But the other thing I can do is I can do things like, this one is really the one I'm interested in right now. Looking at this distribution, how much of this distribution is less than 0? So this is a question of directionality, right? What's the probability that the effect, as I've estimated it, is negative and it's not positive, all right? And so I can just sum all of those observations that are less than 0 and then divide it by the number of observations. That's going to give me the proportion, right? And I see about 94% of all of the parameter estimates are less than 0. Okay, so that's not nothing, but it's not everything either. Okay, and like if we go back to our summary where we were here, you have by default 95% credible intervals for these things as well. So you can see the best estimate is negative 0.31. So that's going to be basically the peak of this distribution. And then the lower and upper bounds of this, you can see it does cross 0, but that's generally going to be a 95% credible interval around that mean, okay? But you have the entire distribution, so you can kind of summarize it however you want, all right? So then another thing I did is I said, okay, I'm going to create a prediction frame. So I'm going to use expand grid. I'm going to do a sequence of schools from -1 to 2 by 0.01 for the mean SES. I'm going to get both girl and boy, and I'm going to just say -999 for my school ID. Then I'm going to add 500 fitted draws from my model, and I'm going to say allow new levels is true because I have -999 for my school ID. So this is going to be population level estimates. Okay, so here's my pred frame. It's going to take a second. And now I can look at that, and it looks like this. Okay, so here's all of these values here for -1 for girls, and then here's a bunch of observations from them, right? And then as we go down, it would go -0.9, 0.99 actually for girls. But you can see we have 301,000 rows. So it's a big data frame because we have 500 draws with this combination, right? And then we have all of those combinations that we specified in this expand grid, all right? So now I'm going to take that pred frame and I'm just going to look at mean SES on the x-axis and the values on the y-axis. And I'm going to use stat line ribbon to give me a sort of most likely relation there, but also the uncertainty around that. Okay. And then I'm going to facet wrap by sex. So I'll get that relation for boys and girls. And then I'm using scale fill brewer to change the palette of that. So I'm using grays, but you could use whatever. And it looks like this. Okay, so here's the relation, the probability of being retained for girls, and here it is for boys. So you can see boys are generally on average higher, but the difference in that interaction is this slope different for boys and girls, right? And that's sort of difficult to tell there. And then of course the shading is for the confidence around that. All right. So that all leads me to this final part where I'm actually interpreting things. One thing I also wanted to note here that I didn't actually include in this, but is that generally in your methods part, not generally, always, if you're fitting something with Bayes, in your methods part, you're going to talk about the model that you're going to fit, but you also need to talk about your priors, okay? And in this case, I used the default flat priors. I'm not sure exactly what all of those are off the top of my head, so I would need to go to the documentation and find out what those priors were, and I would actually include those priors in my explanation of the model that I was fitting. I would say I used the default priors from BRMS. You could or could not say that, it's up to you, but you would definitely want to say I used flat uninformative priors, and then specify, you know, for the fixed effects, they were assumed normal with a mean of 0 and a standard deviation of 10 or whatever it is, okay? So you'd want to specify that so that then people can interpret your model better. And in that case, you might even, depending on the journal you were submitting to and everything, you might even want to say something along the lines of like default flat priors generally allow, well, they do allow the likelihood of in the data to drive the solution. And so therefore, like the point estimates are going to pretty much align with what you would get from maximum likelihood, but then you can look at uncertainty differently and etc. Okay. All right. So finally, I have this right up. I said primary research question, blah, blah, blah. On average, the log odds of being retained were -1.99. And then I have my credible interval for boys and -1.99 plus -0.55, which is -2.54 for girls. And then notice I have that credible interval in there too. And that's from above, right? So I did compute that above, and that's not given to me by my summary output. And that's another one that is different with Bayes, because with maximum likelihood, you would have a 95% confidence interval for the coefficient for girls versus boys, right? But that's actually a confidence interval on the difference between those groups, not on the group itself, right? So these log odds translate to a 12% and 7% chance of being retained respectively, 95% credible interval for both mean and blah, blah, blah. These did cross zero. However, 92 and 94% of the posterior density respectively was below zero, indicating a low likelihood of a positive impact on these things. This indicated that mean SES of the school increased, the likelihood of students being retained decreased on average, right? The mean of the posterior distribution for school mean SES suggests the log odds being retained decreased by 0.33 units for every 1 unit increase in mean SES, right? So that's the same sort of thing that we would get in a standard maximum likelihood model. The only thing that we're doing different is we're saying the mean of the posterior distribution for the thing rather than saying the point estimate, right? For girls, this relation was steeper, blah, blah, blah. And then, yeah, but in some, there's modest evidence to suggest that the higher mean SES at school level was associated with lower odds of being retained, and that this relation was stronger for girls than boys who already had a lower likelihood of being retained. Okay, so, but this part is very much like my conclusions, and other people might disagree with that, and you might disagree with that, and that's fine. The important part is to show the probabilities and then say your conclusions from those probabilities, and that allows people to sort of guide their like if they're unsure, they'll probably just go with what you think, but they also have additional evidence that they can look at to form their own conclusions. Okay, and so that's sort of where this last sentence comes in as like a caveat. However, there's a fairly high amount of uncertainty around these estimates. Okay, so this is just one write-up. I have the other ones down here, and I have some stuff for them too, but I want to stop there in terms of going over the homework, and then I will post this later today, and you'll be able to go and review it yourself if you want, but because I'd like to get to the other content for today. Okay. Any questions on that, though?
I have a question. I still get confused about prior. In the homework, it was okay because we used this flat prior, and I know in the coding. So there's like, I do have some level of understanding. But if we want to use this, like when we say that based on prior research or based on, your literature or, information available. So something like, if a similar study has been conducted 10 years ago and I'm doing something similar, so it's like I'm going by the distribution. One thing I need to keep in mind is the distribution, and if there is mean and standard deviation given around that distribution, I can use that as my prior if I'm conducting similar study 10 years later. Am I right to say that?
Yes. However, it would probably have to be really, really similar to be able to use their exact point estimates. Like you'd have to have measures that are on the same scale. You'd have to have probably similar predictors in the model, etc. So what's probably better but harder to do is to use not just one study, but multiple studies to say, what's the effect size of this thing that I'm studying generally, right? And so if I am going into it and I know, so for example, like with CBM research with oral reading fluency, we've done 4 decades, 5 decades of research on that at this point. And we know with pretty high degree of certainty, kids are going to grow about, like in first grade, like about 1 word per week, right? So I could go into it with a prior saying, I'm expecting kids to grow about 1 word per week. And then the standard deviation of that would just be how confident I am in that. And in that case, I'm pretty darn confident. So I'd probably set it pretty tight, like 0.4, maybe a standard deviation point, maybe even like 0.2, right? However, the other thing to keep in mind is, and there are actually tools out there. I'll see if I can find them. I've only seen them in passing. There are tools where you can say, okay, I expect this effect to be 40% of the time, and I'm 90% confident it's going to be less than 70% of the time, or whatever, right? In more of like a dichotomous one. And there's tools out there where you can specify things like that in more natural language, and they will give you a distribution that you can use as your prior. So that's really helpful also. However, the other thing to keep in mind is your final estimation is a compromise between your prior information and your likelihood of your data, right? And in many, many cases, so for me, it depends on your field for sure. But for me, the data I use regularly has several thousand cases. It doesn't matter what prior I set. They're always going to get swamped by the likelihood of the data. So I end up functionally not worrying about priors that much because unless I set insanely stringent priors, like really informative priors, they just get swamped by the likelihood. And so it doesn't really matter. I can set really broad, I can set really tight, and I'll get almost the exact same answer. Okay, so there's that. If you have less data, so like maybe 100 or 200 or even like 50, then your prior, like the smaller your data set, the more important your priors become. And if you have a really small data set, that's where priors can be really helpful, because you can actually estimate things that you wouldn't be able to estimate otherwise because you don't have enough information in your data. And so you sort of provide more information through your priors, and then you're able to estimate it.
Is there any limit when we are saying small data set or big data set, like above 500, above 1,000?
No, because it's really going to depend on what it is that you're fitting. Because the other thing is, even with large data, right, some things are still going to be really difficult to estimate, like interactions and three-way interactions and things like that. So because the sample size for that specific thing is still going to be pretty low, right? And so I actually just saw a paper, or was reminded of a paper that came out a few years ago from Andrew Gelman, who they estimated that you need 7 times the sample size to estimate an interaction that you do a normal fixed effect. So that's a case where I'm sort of going against what I said before. Even though you have a large data set, there might be specific parameters, depending on what you're estimating, that your priors are going to matter. But yeah, I don't think there's any rule. Like, I've never heard anybody say basically what I just said, which is don't worry about your priors when your data set gets too large. So you're always going to want to think about them. And like I said, you'll always report them. But if you're doing something that's not a super complicated model and you have a large amount of data, at least in my experience, your priors are not going to really matter.
Yeah. Thank you.
There could be other situations, like with interactions and things, where that's not the case. Okay, any other questions or things people want to check in on? All right. Okay, so research questions to model practice. So let's start with, we're going to use that actually 2 data sets throughout this. We're going to start with the alcohol adolescence.csv data set. So please grab that. Also, giving you 2 minutes to get all set up here and load this data set. There should be new data sets on Canvas as well. So make sure that you grab those if you haven't. Alrighty. So here's what the data looks like, right? We have ID, age, COA, which stands for child of an alcoholic, male, alk use, which is their alcohol use, and then peer, which is a measure of the alcohol use of their peer group. Okay. So research question 1, does alcohol use increase with age? Okay, so this is one of those ones where there is not one specific correct answer. Okay, but there are some that are more correct than others. All right, so this is how I would start. I would first estimate the model that makes the most theoretical sense to me, okay, which would be a random intercepts and random slopes model. Okay, if the model fits fine and everything looks good, great. I would just go forward with that model. All right. If I run into model convergence issues and things, or if maybe the variance in the slope is really, really small or something along those lines, then I would sort of go backwards and try to simplify the model. All right. But from my perspective, it makes the most sense to think that every kid is going to have a different baseline, like starting point, and every kid is going to have their own trajectory. All right. So that's where I would start, which means it's going to look like this. Okay, we're going to load LME4, and then I'm going to take ALK, and I'm going to mutate to change age. All right, and I'm doing this just to make the intercept more interpretable. So I'm subtracting 14 from every kid, and that means that 0 represents the age, that represents a 14-year-old kid, all right, which is where they're starting. Then I'm fitting my model. I use Elmer, ALKUSE, age C, plus 1 plus age C. Obviously, I could drop this whole first part, but I'm being a little explicit here. And then data is equal to ALK. Okay, any questions on that? All right, and that model actually does fit fine, as we can see here, and the variance is pretty high on both of those. We've got a good correlation, so it estimated well, so I would just go forward with that one. All right, research question 2. Do children of alcoholics have higher levels of alcohol use? Okay, so keyword here is levels, okay, which implies a change in intercept, not the slope. All right, so the levels mean whatever the slope is, it's just going to move up and down on the y-axis. All right, so that means we're just going to have age C, because we're still fitting the same model we had before, but we're just going to add COA as a predictor to it. Okay. Research question 3. Do male children of alcoholics have higher alcohol use than female children of alcoholics? All right. In this case, we're specifically interested in when COA, child of an alcoholic, is equal to 1. All right. However, to get that, we have to model both 0 and 1. All right. And then within that COA equals 1 group, we want to look at differences between male and female. Okay. So that implies we're going to have to model all 3 of those things: COA, male, and the interaction between those things. All right. So we can do it like this, as I have up there, or we could also just do HC times, not HC, sorry, COA times male. All right, so now we have one slope, and then we have a difference in the intercept, basically, for whether or not they're a child of an alcoholic. Another like offset based on whether they're male or not. And then a third offset for the interaction between those 2 things, okay? But importantly, right, age C is still like our x-axis. So this is all like still just changing in levels, all of this stuff. And we won't get a change in that slope unless we have an interaction with that thing, with this. Okay, we do have, I mean, this is a change in, you know, this slope, although it's like a binary thing, so. Okay, does that sort of make sense? I mean, you could conceptualize any of them as the x-axis, but I tend to just, when we're fitting growth models, always think of time as the x-axis. All right, research question 4. Do adolescents' alcohol use trajectories differ between males and females? Okay, this is not an extension of the previous model. This is a different model. All right, so this is our first one that is specifically talking about differences in the slope over time, right? So now we have age C, we have male, and then we have the interaction between those things. All right, so again, this could be age C times male, and we could omit this part. Any questions on that?
Yeah, I have a quick question on that. So, you know, you mentioned that this is a break in the pattern, or sort of, this isn't necessarily an extension from the first 3 research questions. What's the indicator that it's not an extension? Like I keep defaulting to just wanting to start with a really basic model and get more and more and more complex.
Yeah, so generally, when I'm working on a research project, that is kind of how I do it. Like I start with a basic question, and then I complexify the model more and more until I get to the final thing. The reason I said this is not an extension of the previous model is because this doesn't include COA, right? So it doesn't have child of an alcoholic in the model. So that was all I was trying to clarify there.
Gotcha. Thanks.
Yep. Okay. Research question 5. Does the trajectory of alcohol use differ for male children of alcoholics than female children of alcoholics? This is close to one we had before, but not the same. Okay, this one's the trickiest one we've had so far. This is actually a 3-way interaction. All right, so we have age, child of an alcoholic, and male in there. But then we also have the interactions among all of those things. Okay, and the reason is because we're asking if the trajectory, which is defined by HC, of alcohol use differs for males, which would be this, right? Children of alcoholics, which would be this, okay? And to sort of properly parse all of that, we have to also have these other ones in there, okay? So when you do a 3-way interaction, you have to do, or you should be generally doing all the 2-way interactions as well. Okay, so this is sort of a lot, but we could also specify it like this, same syntax, right? And if we look at the results, you will see these two coefficients flip based on just the way that I've coded it, but the models are exactly the same. All right, so this syntax or this syntax, this is a little more specific. This is giving you all the same stuff. All right. Okay, we're going to switch to new data. So we're going to use the 3lev.csv, and we're going to fit a couple models there, and then we'll move on to other things. Okay, so I'll give you 1 minute to get that data set loaded. Okay, so that should look like this. Here's what the data look like: school ID, student ID, the size of the school, the proportion of low-income students, the proportion of kids who have some mobility indicator, and then some demographics and whether or not they were retained. Okay. So research question 1, 1 minute for this one. To what extent do math scores and changes in math scores vary between students versus between schools? Wait a minute. Math scores and do we have math in here? Where is math? Do you see math in yours? Maybe it's just cut off here.
It's all the way on the end.
Okay.
Yeah, we got it. It's
All right, 1 minute. Okay, so this is a really complicated question. It's more complicated than it probably seems on the surface. We have to do this in 2 parts, and I'm going to actually, like, I'm assuming you just fit the model, right? But to actually do this well, we want to sort of first estimate the model and then do stuff with that model. So we could, I'm saying ICC, it's probably not actually the ICC. We really probably just want to look at the proportion of the variance at those different levels, okay? So here's the model. This is basically what I was expecting you to fit with the model. Math as the outcome, intercept, and then year, and then allowing the intercept and the year to vary by SID and by school ID, okay? So then you have intercept variance and slope variance, and you're looking at both of those things for students and for schools. All right. In terms of the variances, this is one way we can pull those variances. Okay, I say as.data.frame, and then I use this var core on my model, and that'll give me the group, and then the variables, and then the variance or covariance, depending on what it is. So like this is a variance, this is a variance, this is a covariance, right? And then SD core is the same thing, but it's standard deviations and correlations, right? So here's standard deviation, correlation. All right. So what I can do from here now is I can just say, okay, well, give me the proportion on each of those, where I'd take V cove divided by the sum of V cove. So this is like this variance divided by the total variance, right? And I can see about 54% of the total variability is at the student intercept level. Okay, so 54% of the total variability is between students at their starting point. Okay, and less than 1% of the variance is between students in terms of the rate at which they grow. Similarly, we see about 14% of the total variance is initial starting point between schools. And again, less than 1% of the variance is in changes over time between schools. Okay, we can see about 25% of the variance is unaccounted for, residual variance. We can plot this. So this is not the prettiest plot, but it does give you a basic idea. If I just take that same thing I had before, compute the proportion. Okay, so this is just what I had on the last slide. I can go to ggplot, put the group on the x-axis, put the proportion on the y-axis, then call geom_call, and then say fill by var1. So if I look back here, var1 is this thing, right? One of these is NA, that's residual. And so then we can see this sort of coral color is the intercept, the proportion of the total variability related to the intercept for students versus schools. This is our residual variance. And then this little teeny greenish bar down here is the slope variance. Obviously, I didn't expect you to do all of that. But. Okay, research question 2. I think we have 2 more, this one and one more, I think. What is the average difference in math scores among students coded Black or Hispanic versus those who are not? Average difference. Okay, so this is how I did this. I did extend the previous model. This doesn't actually say that it needs to extend the previous model. So if you didn't have year in here at all, then that is actually still probably addressing the research question. But I thought it was important to include year because we still expect some sort of trajectory, right? And so this is estimating now the average difference between students who are coded Black and students who are coded Hispanic versus students who are coded neither of those things. All right. So this is going to be the estimate for the difference between students coded Black and non-Black. And this is going to be the difference between students coded Hispanic versus non-Hispanic. Okay. And then everything else is the same. I had to put this on there to get it to estimate without warnings. Questions on that? All right, last one. This one's quite complicated as well. To what extent do the differences in gains between students coded Black or Hispanic versus those who are not vary between schools? Okay, so you have gains for students who are coded Black, gains for students who are coded Hispanic, and gains for students who are coded neither of those things. To what extent do those gains differ between schools? All right. This model is also difficult to fit. I don't think I got it to fit without convergence warnings. So Bayes might be helpful, but I just went on anyway. Okay, so we have year Black and Hispanic. So those are our fixed effects for those same things that we talked about before. Then we have year Black interaction. Okay, so this is the difference in the slope for year for students who are coded non-Black versus the slope for students who are coded Black. All right, that's what this represents. This is the same thing, but now for Hispanic students. So this is students who were coded Hispanic, the difference in their slope from the slope for students coded non-Hispanic, non-Black. Okay, so these are both differences. That's how all coefficients are, right? But this is the slope. Now these are the differences in that slope for these groups as compared to the group that is neither of those things. All right. Then we have year varying by SID, and then this is the part where we get to what extent do those differences vary between school. Okay, so we have how much does the slope vary between schools, and now how much does the difference in the slope for students coded Black vary between schools, and how much does the difference in the slope for students who are coded Hispanic vary between schools. Okay, so if you're thinking about this in terms of like achievement differences, right? You might actually, and probably would actually want to include both of these in there too. So you'd have basically everything varying at the school level, which is a really complex model and might be overly complex. but then you could estimate how, like, what's the initial starting point for students among these three groups, and then to what extent do those differences increase or decrease over time within a specific school. And so you could imagine, depending on the policies and things, in some schools, those initial differences grow, and in other schools, those initial differences close. Okay? So that's a really complicated model, but also pretty powerful in terms of what it can address. So yeah, this is just a note to say that we have very low variances, and so that's why we're having convergence issues here. Okay, so that's it for that part. Before we move on, are there any questions on any of that? All right. Okay, so finishing up from last class, I'm gonna go through most of this quite quickly until we get to the part that we haven't covered, all right? But I wanted to have enough of a ramp up so you could kind of remember what we're doing. Okay, so this is the HDP data. So this was lung cancer data, and we were looking at the probability of remission, all right? So we have these different variables, and we're gonna build a model where age, lung capacity, and tumor size all predict whether or not the patient went into remission, okay? So we build the model so we can evaluate whether or not the relation between tumor size and the likelihood of remission depends on age. Okay, so that's an interaction. And then we also wanted to allow the intercept to vary by doctor. So we're expecting that the doctor is going to play a role in this, and so we want to account for that variance. We fit the model using BRMS. This is interesting. That was not there before. It almost looks like one of those memes of like somebody falling off a building or something. Okay, so this is the model though, right? We have age times tumor size. So this is going to be the fixed effect for age, the mean effect for age, and mean effect for tumor size, and then the interaction between those two things, plus lung capacity, and then we have the intercept randomly varying across doctor ID. The data is HDP, and then the family is Bernoulli with the logit link, 4 cores, command stand backend to make it faster. All right, then we're going to look at variance by doctor. Okay, so starting with looking at the relation between age and the probability of remission for each of the first 9 doctors. Okay, so I'm using tidy Bayes here again, and I'm saying expand.grid, give me the first 9 doctors. I'm just using 1 to 9 here because that's how the doctors are ordered. And then age going from 20 to 80 years old. So very big range in age. For tumor size and lung capacity, I'm just setting those at the means. All right, so this is the equivalent of like a marginal effect. All right, then I'm adding 100 fitted draws to this model. I can look at it like this, right? So here's DID1 for age 20, and then it would go DID1 for age 21, DID1 for age 22, all the way up to DID1 for age 80. And then it would switch to DID2 for age 20, DID2 for age 21. And for each of those combinations, we're getting 100 draws from the posterior distribution. All right, so over here is the dot value, which you can't see, is the actual draw, okay? And then we can plot these like this, all right? So we have the predicted, or this is our data frame. We have the age on the x-axis, which ranges, from 20 to 80. Dot value, so that's the actual posterior draw. And then we add a geom line where we're saying the group is equal to dot draw, all right? So back here, dot draw is like essentially an ID for the draw from the posterior distribution. I'm adding some alpha here too, pretty high level of alpha, so that you can get sort of an estimate of or you can kind of see how the likelihood decreases. And then facet wrap by DID. So you can see just by looking at these first 9 doctors, there's a lot of variability across doctors, right? With this first doctor, you have a very low likelihood of remission, of going into remission pretty much anywhere, right? Regardless of your age. For doctor 2, you have a pretty high likelihood of going into remission if you're young. And then that likelihood obviously decreases as you get older. Same for Dr. 3. We've got more variation though. So we're sort of less certain about the effect for Dr. 3 than we are for Dr. 2, right? But you can see there's quite a bit of variability here. We can look at our variables. So this is from Tidy Bayes. We can use this get variables, and we see we have a whole bunch of different parameters, right? And specifically, we have this RDID, and so this is the random effect for each doctor. So we can, this is like the first to the nth doctor, and then this is the estimate for the intercept, which was the only thing we had randomly varying here. Okay. So multiple comparisons. One of the really nice things about Bayes is that we can look at all sorts of different comparisons without having to worry about adjusting alpha and all of these other things that we typically have to worry about. So we're going to look at this for a scenario. This is what we did last time, but we're going to go through the whole thing this time, where we have a 35-year-old person who has a tumor measuring 58 millimeters and a lung capacity of 0.81. Okay, so our question is, what's the likelihood of this person, given our model, going into remission if they have the first doctor versus the second doctor? And just looking back here, we can expect that there's going to be a higher likelihood of being in remission with the second doctor than the first doctor, right? But we want to actually estimate that directly. Okay, so here's how I would start this, right? First, we can use spread draws from Tidy Bayes to get all of the sort of averages, the distribution of all the averages from our model. So we're saying intercept, age, tumor size, lung capacity, and then that interaction that we estimated. All right, and I'm using spread draws, which means I'm going to get a new column for each of these things. If I used gather draws instead, I would have one column for the parameter, and that would sort of list B intercept, B age, B tumor size, and then we'd get the value as a second column. Okay, so we'd have two columns, whereas here we're getting a new column for each thing we add on there. Okay, so that's the difference between spread draws and gather draws. Then we create our data for our person, and we're going to first create our population level distribution. So this is where I'm just now taking all of those fixed effects I had, right? And I'm going to add them all together, where I'm multiplying each coefficient by the actual data that we have here for our person. Okay, so if we look at the distribution of that, this is our population level estimate of the odds of going into remission, log odds technically. All right, so this is sort of independent of doctor. We're not accounting for the doctor. We're just saying if we had a 35-year-old and all of that those other things, so 35-year-old with 58 millimeter tumor with 0.81 lung capacity, then this is like the log odds of going into remission if we don't know who their doctor is. We're just estimating generally, okay? However, if we want to know what the odds are between different doctors, then we can actually include that information. Okay, so here I have DIDs. I'm saying spread draws, where I'm saying give me all of the doctors. Give me all the random effects for each doctor. Okay, so that's what this is doing here, which we can get this information basically from that show variables or whatever it was, get variables. And then DID, whatever I put there, that's just going to be the name of the column there. All right, and then this is saying for all of the parameters, there's only one parameter, which is intercept. Okay, so then this is all of the doctors, and now I'm just saying, okay, filter that, give me just the first doctor, and then filter that again, give me just the second doctor. So I have the first doctor and the second doctor, and this is the entire posterior distribution for each of those. Okay, then I'm going to actually add those to my population level prediction. So I have one population level prediction, or I have the population level prediction distribution, right, this thing. Then I'm going to add to that distribution DID1, and then as a second object, I'm going to add to that distribution DID2. All right. Here, I'm just putting those together. So I'm saying, okay, now rep 1 to 2, each the length of pred DID. So that's going to go 1, 1, 1, 1, 1, and then until I get to the second doctor, and then it's going to go 2, 2, 2, 2, 2, 2. And then I'm going to put together my pred for DID 1 and 2. So this is just a way to put it all in a data frame. All right. Once I have it in a data frame, then I can do all my normal data frame stuff. So I have DID 1, 2. I'm going to group by DID and summarize to give me the median. So here's the median log odds for Dr. 1 for the log odds of remission. And here's the median for Dr. 2. So 0 is going to be sort of our 50-50 point. So you can see this is really far different. And this is actually, we're saying you have a greater than 50% chance of survival, or not survival, remission with Dr. ID 2, whereas you have a very low likelihood with Dr. ID 1. And that confirms sort of what we would have seen before, but we might want to do additional work here. So first thing we could do is just plot that. And this is helpful because now we see how sort of certain we are about these predictions. And so you can see for DID 1, the entire distribution is negative, right? If here's 0, the entire distribution is negative, but it's also pretty big spread, right? So there's a lot of variance in that. So we're not like real certain of the point estimate for this doctor. With this one, all of that posterior probability density is sort of jammed together. So we're actually quite confident this is, it's going to be somewhere in this range, we think, right? So that's helpful. But what might be even more interpretable is to go ahead and just transform from the log odds scale to the probability scale. And so we use BRMS inverse logit scaled on this to do that. And so here, this is just the exact same code I used before, but now I'm using inverse logit scaled on pred here and on the medians for the lines. And now we get something like this. Okay, so this 0 is like, obviously there's a 0% chance, whereas here there's 50%, right? So as expected, the sort of median of this posterior distribution is above 50%. And so you can see on a more interpretable scale, like what the odds of going into remission are for these two doctors. Okay, and so this should very strongly communicate that you want Dr. ID 2 here. You don't want Dr. ID 1 if you have cancer, lung cancer in this case. All right. We can also do things like compute the difference between these. So we can look at the median difference by just computing the difference in the medians, and we get 3.58. Okay, so that's cool. But we can also, because we're on the log odds, anytime you have a log, you can exponentiate it to get it back to the original scale. All right, so I can look at these things on the probability scale, and I get about a 4%. The median likelihood of remission is about 4% for DID 1, and it's about 60% for DID 2, 59%. But if I exponentiate those things, then it transforms it to from log odds to odds. Okay, and if you're into gambling, you probably know what odds are. If you don't, you probably don't. I don't really know odds all that well, but they center on 1. I can tell you that. Right, and so here the odds of remission versus not remission is 0.04 and 1.45. That's still probably not that interpretable, but what is interpretable is if we exponentiate the difference, then we get a value of 36. And what we're saying in this case is that the odds of going into remission for our theoretical patients are 36 times more likely if you have DID 2 than if you have DID 1. Okay, and so that's a good way to communicate this information. We're saying you are 36 times more likely to go into remission if you have DID 2 than you have DID 1. And that value actually makes quite a bit of sense if you think about our distributions and how far separated they were on the probability scale and all of that sort of stuff. Okay, I'm going to pause there for a second. Questions on this? Is this making sense? Okay, please do feel free to interrupt me as I'm going here if it's not making sense. I am going fairly quickly through most of this. All right, so we have a difference now between these, but we actually only looked at the difference in the median, like the difference in the two medians between those distributions. All right, and remember that in Bayes, everything is a distribution. So what we can do is we can actually just compute the difference between those two distributions, and we will again get a new distribution. And that is super nice because we can do things like say, here's the difference, here's what we think is the difference between these two doctors, but here's the uncertainty around that difference as well, okay? And that's a really nice thing that you can get immediately without any additional work in Bayes that would be much more difficult to get through a maximum likelihood approach. And either you would have to do a whole bunch of really complicated math, or you would probably actually end up just simulating and getting essentially the same sort of approach that we're getting here, okay? So what we can do is just compute the difference between those. So here I'm creating a DI tibble, which I'm calling DID2 wider, 1, 2 wider. So I'm just saying here's DID1, it's pred DID1. Here's DID2, it's pred DID2. And then I'm mutating to compute the diff in those, which is just DID1 or 2 minus DID1. Okay, so here's what my tibble looks like. Here's the posterior draws for DID1. Here's the posterior draws from DID2. And here's the difference between those. So it's just the difference on each of these. Okay. Now I can summarize the difference in that distribution. So if I look at the lower bound of a 95% credible interval, the median, and then the upper bound. So this is a 95% credible interval around the median, basically. Then we get something like this. So the lower bound is 4.79, right? Which is still really big. The upper bound is 600, which is like crazy. And here, and this is, I've exponentiated this, right? So this is odds, again, not log odds. But even at the very lower bound, we're saying you're about 4.8 times more likely to go into remission with Dr. ID2 than you are with Dr. ID1. This is our median, right, that we had before, about 36, 37 times more likely. And then, but at the upper bound, we're saying you're 600 times more likely, which is just like craziness, right? So we can actually plot this distribution. This is exp diff, right? So this is the exponentiation of those differences. And so you can get a distribution of the odds and the likelihood of those. Okay, so when you're exponentiating, obviously everything is going to be above 0. You could look at this on the log odds as well, and then it would look much more like a normal distribution. But I think odds are a little bit more interpretable here, so that's why I did that. Okay, this filtering part is just to look at the 95% credible interval. So I've omitted the lower 2.5% and the upper 2.5% in this distribution. So you could choose to do that or not, but there were a couple that were like on this side that were way extreme outliers if I didn't cut it. So that's why I did that. Okay. Also, we can do things like look at directionality. So I've done this a couple of times now, but I just want to highlight again. Is there a greater chance of remission with DID2 than 1? Well, we've done a lot now that gives us the answer to that, which is yes, right? But if we just want to know if the difference is positive, we can say, are there like, how many of these are positive divided by how many we have? And we have 4,000 because we have 1,000 draws from each of 4 chains, right? And when we estimate it, we actually estimate 2,000 for each chain, but remember we cut off that first 1,000, just throw them away because of random starting points and all that sort of stuff. So that's the burn-in period. Okay, so we get 1 here. We don't have a single difference that is less than 0. Okay, meaning we don't have a single observation where DID1, we think that the odds of, or the likelihood of remission for Dr. ID1 is greater than Dr. ID2. So we are as confident as we can be that the odds of remission are going to be higher for Dr. ID2 than Dr. ID1, given our model, right? And that's a really important caveat, given our model, because our model could be wrong, right? Okay, but one more quick example, because that one is a little bit less than ideal for that specific situation. Let's look at DID2 and 3. Okay, so if you remember back, DID2 had way higher likelihood than DID1, but DID2 and 3 were both pretty high. DID3 was actually even a little higher, but it had more uncertainty. Okay, so here I'm going back to this original DIDs thing, and I'm just grabbing DID3. All right, then I'm getting the predictions for DID3 by taking the population level and adding DID3 in there. And then I'm doing the same wider thing I did before. I'm getting rid of DID1 though, and I'm getting rid of the diff. And then I'm mutating to add DID3 in there and then compute the diff, which is now the difference between DID3 and DID2. Okay, and so that looks like this now. We have DID2, DID3, and then the difference between those things. Now, if we do that same thing we did before, we get this, which means in this case that there's about an 86% chance that the odds of remission are higher with DID3 than 2. Okay, so 86% chance. So that's not 100% chance, right? But this is, I think, a good example of why interpreting these things in terms of probability is helpful, right? We're able to make these really nuanced comparisons between doctors, and we can talk about those differences in terms of probability. All right, so we can plot the data. This is how I've chosen to do it. I'm using pivot longer, and then I'm saying the names are to distribution, the values are to log odds. So here's the distribution. We have DID2, DID3, and the difference between those things, okay? And then we have the log odds here. All right, and then this looks like this. So you can see the median of these two distributions are separated, right? And DID3 is higher than DID2. But there's also more uncertainty around DID3 than there is DID2, okay? And so so that's where we get this 86% thing rather than like 100% we had before. This is the distribution of the difference on the log odds scale, okay? And again, here's 0, so most likely DID3, okay? And then we can also put that same thing on probability scale if we wanted to, and there it is. The distributions look a little skewed because that's not the linear scale. Okay, so that's it before we go to break, but are there any questions on that? That's finishing up what we did last time. Hopefully that is a pretty good example of why this framework of Bayes can be very powerful. Okay, I think it's super neat, but that's just me. Okay, so let's take a break. We'll break for 5 minutes. We'll come back and we'll talk about non-nested models. Okay. All right, off we go again. So we're going to talk about missing data first. And as I mentioned before, this is going to be quicker than I would like it to be, but that's the way it is. So missing data is not really a multi-level modeling topic. It is a massive topic on its own. And so I'm sort of hoping that you've covered this some in other classes. So this is going to be mostly about sort of implementation options. Okay. If you have missing data on the dependent variable, that tends to be, at least in my experience, mostly what we usually talk about. And there are lots of ways to handle that. Just standard maximum likelihood is usually going to do a pretty good job of handling that, of sort of marginalizing across the missing data. If we can assume a missing at random process, so missing at random conditional on the observed data, conditional on the covariates, then most modern methods will do a pretty good job. Missing data on the independent variables tends to be a lot more challenging problem, okay? And this is true no matter what model you have, no matter what application you have, it's always going to be a much more difficult problem, okay? One of the things we often do is just remove any cases that have any missingness on the independent variable. This does limit your sample size a lot, and it probably also introduces sources of bias. That's what many people refer to as list-wise deletion, okay? The other alternative is you can impute, and those are pretty much the only two options, right? You either have to get rid of the missingness or you have to impute to account for the missingness. Imputing is also often very challenging, and there are ethical challenges there too, okay? So think about gender. Do you really want to impute somebody's gender? or their race ethnicity, right? That makes me feel really icky. So then that might leave you to kind of feel like this, where you just want to give up. Like, what am I going to do here, right? So there is no real good solution. What you can do is be very clear about the decisions that you make, right? If you do choose imputation, then you should use multiple imputation, all right? This will, in addition to generally working better, will also allow you to have some uncertainty in your imputation process that you can use and at least communicate, all right? The purpose also, when you're doing imputation, should be, and generally is, to get unbiased population estimates for your parameters, okay? Not to make inferences about those individuals for whom the data were imputed. And so that's a really different frame, and that can help a little bit, I think, with these ethical challenges. It doesn't alleviate them by any means, but if you're clear about why you're doing it and that you're trying to get unbiased estimates of sort of the mean effect of something, right? Not making inferences about a specific individual, then imputation, I think, makes more sense. All right. If you have missing data on the ID variables, I don't know what to tell you. I don't think there is anything that you can really do. There has been some work on this. It's not like it's completely like people are just giving up. But I have not seen a solution personally that I would feel comfortable with. So this is super common in multi-level designs. And this is one area where the missing data is specific to multi-level modeling, right? You have to have ID variables to link your observations to those higher levels. So for instance, you have a student and you have to link that student to a school, right? If you have longitudinal data, which is where this becomes really common, you might have data on a specific student, but you don't have the ID that links them to the specific school. Or if you're going down to like a teacher level, that's even more common, that you can have data without a teacher ID, all right? And so if you're missing those IDs, I don't know what to do. I mean, there are some cases where you can make some assumptions and impute. But so, for example, if you have longitudinal data, right, and you have, it's like 3rd, 4th, 5th grade, right? Let's say you have 3 observations in each of those years. If you have, for a specific student, you don't have their school ID for any of the data collected in 3rd grade, but you have it for 4th and 5th grade, and it's the same school, you could make the assumption that it was the same school in 3rd grade too. And maybe you know why you don't have that linking data in 3rd grade. However, that's still a pretty big assumption, right? And so you would for sure want to communicate what you're doing there when you're making that assumption. And the other thing that is problematic about that is that you know, those decisions can really change your model, right? So whether you omit those or whether you assume they're from a specific school or whatever. The other thing that I don't have in here, but is also common with longitudinal data, is you can have shifting demographic variables. And so you have to be really careful about how you're going to handle that if you're including those demographic variables in your model. So for example, we had data, statewide data, where we did have things like gender changing over years, right? And you have things like race, ethnicity changing over years. And then there's others that, like, there might even be like instructional reasons why those things are changing over years. Like you have students who are designated with a specific learning disability in one year, and then they are not designated with that learning disability later. So how you handle those things is all going to change how your model works, okay? So this is all to say this is all super, super complicated, right? It's not, there's no easy solutions here to any of this. However, if you are going to go forward with modeling, you need to make some sort of a decision, okay? So as I said during the imputation part, if you have missing data on the IVs and you want to go forward with modeling, then your purpose is probably to get unbiased mean effects, right? What's the unbiased estimate of the average effect of this thing or whatever, right? And so in that case, imputation is probably going to be your best bet. You're probably going to get a closer representation of that using imputation than you would if you do something like listwise deletion. And that's obviously a big statement that isn't always going to hold. And it's going to depend on how many cases you have, how much missing data, the patterns of the missing data, what are the underlying mechanisms of the missingness, all sorts of other stuff, right? But generally, that's going to be the case. And so we'll want to do something like multiple imputation. Okay, so we're going to do it. We're going to do multiple imputation. So this first part is general and it's not specific to multi-level modeling. Okay, first, we're going to install and load the mice package. Okay, there's also the Amelia package, which is also pretty good. All right, so this is the package, though, that I would use if I were going to use multiple imputation. Okay, so I'll give you a second to do that if you want. And then once you have that, can you just give me a thumbs up emoji so I know I'm ready to go on? Okay, that looks like just about everybody. Okay, now from the mice package, we have this NHANES data set, all right? And it comes with a whole bunch of missing data, all right? And in this case, the only thing that's not missing, at least in these first 6 observations, is age, right? And that's probably not our outcome. So we have missing data on the independent variables and the dependent variables, all right? And some, like this one, are missing on all of them, all right? So that seems like a really challenging problem. And it is, but multiple imputation can help it with that problem, all right? So how much missing data? This is optional, but there's another data set called nonlinear. And if we use that, we can call vismiss, and we'll get basically a column for each column in our data set. And then it'll be colored according to whether it's missing or not. So you can kind of visualize your entire data set quickly. And you can see there's a big swath here where they're missing on everything except age. All right. So in order to do this multiple imputation well, we are hoping that age is going to relate strongly to these other variables. All right. Because basically what we're going to do is build a model for to impute each of these observations, like just a linear model that uses the other variables to predict there, right? So for example, we would build a model for where BMI is the outcome, and we would use age, height, and cholesterol, CHL, as predictors in that model, right? Then we would predict from that model to actually impute on the missingness. So we would use the non-missingness here as the outcome to build that model, and then we would predict what those observations would be for the missingness. All right, so we're building like a linear model, and that's how we impute. But with multiple imputation, we do it multiple times. Okay. All right. So how do we do this? First, we're going to create 5 new data sets, each one with the missing data imputed. Okay. And so I say m equals 5 here. All right. And so mice NHANES being the data set I want to impute. M equals 5. That's going to give me 5 new data sets. Print equals false. I just don't want this summary stuff that it's going to give me. All right. And then if I look at MI NHANES was my object, right? And then I look at imp and then BMI. Here's the imputed data for each of the 5 times I did this for BMI. Okay. So for this first observation, I'm first imputing with a value of 30.1, then I'm imputing with a value of 22.7, then I'm imputing with a value of 35.3. So you can see I get like a mean that I can actually use as my final imputation, but I can also get a standard error around that for each of them. Okay. Now, if we want to fit the models, we can actually, so there's multiple ways we can do this now, right? We've now done the multiple imputation. We can get that data back to a single data set if we want to, and we can use that data set just like LME4. However, I'm going to not do that in this case because I'm going to just use BRMS. BRMS has really nice ways of handling missing data. And so that's like sort of the main thing I'm trying to illustrate here, not necessarily this part specifically. Okay, so if we wanted to go to LME4, I think I have some resources somewhere else about how you would do that. But if you just Google, you know, mice LME4 R multiple imputation, you'll find some blog posts and things that'll walk you through that. Okay. But with BRMS, we have this new function we can use called BRM multiple. Okay. And the thing that is super nice about this is that what we can do is I can then specify my formula here and specify my data as just that mice object. Okay. And what it's going to do is instead of like imputing to it down to a single data set, it will actually do a better process, which you could also do with LME4, but it will fit the entire model to each of those 5 data sets. Okay, so it's going to fit the model 5 times. And then from there, we can pull the results down to a single sort of estimate. Okay, so instead of everything else is the exact same. Instead of using BRM, though, we use BRM multiple. And then for our data set, we just specify the mice data set, and it works. You can do this same thing with Amelia too if you use that for your multiple imputation algorithm. Okay. So that's basically it. From there, you could summarize. You could do all the same sort of stuff that you would do normally. Okay. An alternative thing that you can do with BRMS is instead, so that what we just talked about is imputing before estimating, right? But with Bayes, you're doing all of this like random generation anyway. So what you can actually do is use observations from those chains as you're going along to impute on the fly. And then you can actually get a distribution of the missingness for each of those as well. So you get sort of like 1,000 imputations if you're getting 1,000 draws after warm up, right? For each of those observations. This actually generally doesn't work quite as well as always, right? Doesn't always work quite as well as multiple imputation first. However, it's going to be much, much faster because then you can fit the model once rather than fitting it 5 times or however many times you multiply impute. Okay. And for many cases, it does work very well. Okay. So in this case, as we'll see, it ends up working basically exactly as well as multiple imputation. You get pretty much the same results. So we still get uncertainty because of the repeated sampling, and we can do this with BRMS because it's a really powerful package. We do this, though, by specifying missing formulas, okay? And so we specify a model for each column in our data set that has missingness. So we're going to just like I said with multiple imputation, where we essentially are fitting a model each time and then using that model to impute the missingness, we're going to actually specify what those models are going to be. And we have missing in our formula back here. If this is the model that we're fitting, right, we have missingness in BMI and we have missingness in cholesterol, but we do not have missingness in age, right? That was the one column we don't have missingness in, okay? So BMI is our outcome, and it will be modeled by age and the complete, right, missing data imputed, cholesterol variable, all right, as well as their interaction. The missing data in cholesterol will be imputed via a model itself with age as its predictor. Okay, so we're basically fitting two models at once. We fit a model with cholesterol as our outcome and age predicting it. That fills in the missing data. Then we use that within our main model where we're using age and cholesterol to predict BMI. Okay? So this is what this looks like. We are using now something new, which is BF rather than BRM. And all of this that I have here is just to specify the formula. BF stands for Bayes formula, okay? And so we have BMI, our outcome, but we put this little bar here and then say MI. So we're saying this has missingness, so model that missingness, okay? That's our outcome though, and it is modeled by age times cholesterol, just like before, but we're gonna wrap cholesterol in MI. So this is missing data is being imputed. So this is like the complete version of cholesterol, right? And cholesterol itself down here, this is the model for it. Okay, so now this part looks just like up above, except we have cholesterol as our outcome, and that's predicted by age. Okay, so we have two formulas, a Bayes formula for our sort of base model, a Bayes formula for our missingness, and then this set rescore false is just saying don't estimate the residual correlation. I honestly don't totally understand that, except I guess it's hard for it to do it with all of that. So we'll look at that more here in a second. When we fit the model now, we just use BRM instead of BRM multiple because we're just fitting one model. And our formula is going to be Bayes impute formula. So that thing we created back here. Okay, so this is one very complicated formula. We use that here, and then our data is in Haynes. Okay, when we do the comparison, okay, this is the conditional effects for M mice. So this is just looking at the interaction, all right? But this is for mice, and you can see this is what it looks like for these different levels of cholesterol, all right? If we look at that same thing for our on-the-fly results, you can see they look pretty darn similar. And actually, the y-axis is a little bit different here, so that kind of makes them look maybe a little more different than they would otherwise. Okay, so our inferences that we would make from this model, where we've used multiple imputation first, are not any different than this one, right? Those inferences we would make would probably be exactly the same between them. This model is going to be far more computationally efficient. We only have to fit the model once versus 5 times. For this specific model, the data set's so small, it runs really fast anyway, so it doesn't really matter. But as we've seen, Bayes models can take a long time to fit, right? And so this is just an alternative. This on-the-fly part 2, though, is pretty complicated, right? Thinking through all of this and how it's going to work. All right. So that is pretty much all I have for missingness. I know that was fast, but I wanted to at least give you something about missingness because it's a big topic. It's something you're going to run into as you fit these models more, and you have to have, like, you got to handle it some way, right? You got to do something. Either you're going to omit those cases and say, I'm just working with this subsample, and that's probably going to limit the inferences that you can make because you're going to say, I'm only able to make inferences to a population that had complete data, right? Or you have to do some imputation like this, okay? And there's different ways that you can do that. I would probably honestly start by just doing the multiple imputation as I showed here, because that's quite a bit easier, I think. But if it's taking forever to run, then you're probably going to want to look at something like this. Okay. Okay, so Masaki's saying when he ran BRM multiple, he got high values for R hat. So in that case, I would probably just increase the number of or the iterations that you're using. Yep, Chris.
Oh, I see. Thank you.
Yeah, no problem.
I was going to just ask about if you were using a software that didn't like have some sort of built-in capability to handle multiple imputation and pooling the estimates, is that a time when you would use single imputation, or would you run it and kind of pool it yourself somehow?
Yeah, I would still try to run it multiple times and then pool it myself. But it would really depend on the modeling framework, I guess. I don't, yeah, because the way that you would do that would differ, right, depending on which framework you're using. So I don't, yeah, that's not a very good answer, but I would always try to use multiple imputation.
Okay, thanks.
Other questions? All right. I know that was super fast. It's very like surface level, superficial coverage, but at least we covered it a little bit. Okay, cross-classified models, non-nested models, okay? So this, I think, is going to be the last topic we cover today in the last 30 minutes. Everything we've talked about so far in this class assumes a nested structure, okay? So this is a standard nested structure where you have observations and they are nested. So this is one student, 3 observations, another student, they're nested in a teacher in this case, and that teacher is nested in a school, right? And then this student is nested in this teacher, which is nested in this school. And these 2 students are nested in this one teacher who's also nested in this school, right? And same sort of thing over here. I think this is originally a longitudinal design, so this would be like year 1 and year 2. But far more, well, not far more frequently, very often, you end up with non-nested structures, which are also called crossed or cross-classified structures, all right? So here's an example where you now have a student, and this student is not nested in one teacher. They are nested in 2 teachers. Maybe this teacher for the first 3 observations and this teacher for the next 3 observations. Those teachers are both nested in one school, right? But all of these observations are nested in this student, but there is a cross-classification at the teacher level, right? This student is cross-classified between these 2 teachers, all right? Similarly, over here, this student is cross-classified between these 2 teachers. Those teachers are nested in this school, but this teacher is in this school for these 2 observations, or for this observation. Like, so these 2 students are nested in this teacher, but this teacher is like this. Oh, sorry, no. This student was in this, like with this teacher, and then later this teacher, and then they're in this school. Okay, so this student then is cross-classified not only between teachers, but also between schools. Okay, and you could end up with situations also where teachers are moving between schools. So now teachers are not purely nested within schools. They're cross-classified between schools as well. Okay, so this is a very like nested structure in education that is very regularly not nested. Okay, you have students that are moving between teachers, you have students that are moving between schools, and you have teachers that are moving between schools. And as soon as you go longitudinal with any of this stuff, you're almost sure to run into some of this. So again, this is either you have to choose some way to handle this, right? Either you can model this cross classification, or you can omit cases and just only model the nested cases. All right. obviously, if you do that, though, that's going to introduce some degree of bias into your estimates, depending on how much of that you have to omit and how large your data set is, et cetera. Okay. There are also all sorts of other ways that data can become cross-classified. So we're going to fit some models. We're going to go back to LME4. And these are just example data sets that are straight from LME4. So go ahead and load LME4, and then we're going to take penicillin data, and I'm going to arrange it by sample. Okay. And then if you look at the head of it, it will look like this. So here's diameter. I don't remember what this is referring to at all, but we have these two sort of grouping factors: the plate that the sample came from, or that, yeah, the observation came from, and then the sample itself. Okay, so here's sample A, B, C, etc., and then the plate within each of those samples, and then the diameter. Okay, so I'll give you a second to go ahead and load that. Give me a thumbs up emoji once you're ready there. All right. Now we're going to fit a nested model. Okay, so we have diameter. We're going to model an intercept, and we're going to let that intercept vary randomly across samples. Okay, go ahead and do that. And we can tell that this is a nested sample by looking at the residual variance covariance matrix. Okay, so if you load sundry, you can say poll residual v cov on this nested one, and if you pass that to image, you'll see something that looks like this, right? So this is what we talked about before, but now we have basically the diagonal is going to be ones, right? And then this is the covariance part of it. Okay, the reason that I arranged by sample was because I was going to fit this model, and if I didn't arrange by sample, then we wouldn't get this block structure like this. Okay, so we can tell that this is nested because we have this block structure, right? Block, 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 block. Everything's good, right? Nothing on the off diagonals. Okay, so nothing in this area. That means it's nested. All right. Now we're going to arrange by plate instead. So we're going back to our sort of before. And this is the way it's arranged originally. And now I'm going to fit the model, but I'm saying one sample, one plate. Okay, so I'm allowing the intercept to randomly vary by sample and by plate. Okay, and if I pull the residual variance covariance matrix here, I get something that looks like this below, which is very clearly not nested. Okay, because you can see we have this block diagonal here, but we also have these stripes, right? And this is like, the way that this image looks will depend on how you're sorting things. That's why I've arranged each time differently. But you can see we have all of these things that are being estimated on the off block diagonal as well. Okay, that is a non-nested model then. Okay, we can get a closer look like this. So I'm pulling the residual variance covariance matrix, and then I'm just pulling the first 12 of each of these. Okay, so here's the first block diagonal, and here's the second block diagonal, and you can see in between them we're also estimating this variance here. Okay, so that's what's going on in this model. All right, we're estimating the block diagonal, but also these off block diagonal things. Okay, I don't have this here. Darn it, I thought I did. Let me actually move to RStudio for just a second. Okay, let me go to here. All right. Pull over here. All right, LME4 penicillin, head penicillin, and then we're going to fit, let me go to the cross-classified model, copy all this code. Oops, that's not what I want. I want, well, whatever, I'll just grab this one. Actually, I probably do want this part too. Okay, so I fit the crossed one. It fits amazingly fast, right? This is where LME4 is pretty darn impressive. There are other packages and things out there that are just as fast, but if you're coming from like the HLM world that you used last semester, right? This model would take probably several minutes to fit, and it's like instantaneous here. If we look at the summary of this, then you can see we have independent variance estimates for these two things. Okay, so we can say, right, the intercept is 22.97, and this is like in such a different world than what I typically work in. I have a hard time interpreting what that even means. But the average diameter, whatever that means, was 22.97, and that varied between plates with a standard deviation of 0.84 and between samples with a standard deviation of 1.3 or 93. And so even though those things are not nested, we can still interpret that in the same sort of way. Okay, so that's pretty neat. Doesn't solve our issue that we were talking about before with the non-nestedness of students between schools and things, though. And we will talk more about that, though, in just a second. Okay, one more quick example. This is again straight from the LME4 documentation, but we're going to use the oxide data now, which is from the NLME package. Okay, so oxide looks like this. This is a 3-level model. So we have thickness, we have lot, and wafer. I have no idea what this stuff means, but whatever. So go ahead and get that loaded. Okay. And now we can do something like this. So I have lot slash wafer. Okay. So I'm saying these data are nested, lot within wafer. All right. And if I fit this model like this and I pull the residual variance covariance matrix, you can see I get this is now like a 3-level structure where I have these little blocks within this big block, right? Little blocks within the big block for each of them. Okay, so that's a purely nested 3-level model. Cool? All right. What if, though, we changed our notation to look like this? Well, then, if we pull our residual variance covariance matrix, we get this sort of thing. And this is incorrect in this case. We have modeled a cross-classified model, a non-nested model, when in fact they are nested. Okay, so I mentioned this before when we were looking at I think our first 3-level model that we looked at with LME4. But the IDs need to be unique if you're going to use this syntax. And I do use this syntax always because I am very particular about my IDs as well. And I always know that they are unique. And so I always use this sort of syntax because I kind of like to keep them separate. However, this is safer to purely define them as nested. Okay. So let's look back here at this. What I mean by this is, right, we have lot and wafer. And so this is going to go 1, 2, 3, and then lot will change to 2, and then wafer will go 1, 2, 3 again. So the wafer ID is not unique. All right. So what I would tend to do, if this were me, is I would fix the data rather than relying on model syntax. Okay. So the model is the same regardless of the model syntax. So this is how I would do this. I'm taking oxide, I'm changing wafer, so I'm pasting lot and wafer together, all right? Then when I fit this exact same thing, I can pull the residual variance covariance matrix, and now I get that same sort of structure, okay? And then you can tell if I look at the nested syntax, there's my results. If I look at the other syntax like this, there's my results. We can go back and forth between them, and you can see they are exactly the same. Okay. All right. Now, moving on to more like the example that I started with, which is where I have dealt with cross-classification most of the time, which is things like, not always, but things like switching schools, right? So you have longitudinal data and students switch schools over time, or they switch teachers over time, or whatever, okay? There's a paper here that I've linked to that is specific for BRMS. It was written by the guy who wrote BRMS, and it talks about multiple membership models and other things. So it's going to give you a lot more depth than I'm going to be able to do here in 15 minutes. All right. But let's go ahead and do this. So there should be pupils.csv now in the data. So what we're going to go ahead and load that. Okay. So go ahead and do that, and then give me a thumbs up emoji when you've got it done, and I will move on. Okay, seems like most people, but I'll give it 30 more seconds or so. All right, I'm going to just assume that most people who want to follow along are ready. Okay, so about the data, these are data that are very classical cross-classified data. If you look into the literature for cross-classified random effects models or non-nested multi-level models or whatever, this will come up a lot, all right? They are students who transitioned from primary to secondary schools, all right? And we don't know how long they spent in each school. And these are actually not longitudinal data, which makes the problem much easier, okay? But it's when we are looking at their final score. So I don't know what the score is, but we could imagine that secondary schools mean like high schools, and that this is like some high school exit exam, all right? And we have their scores, we have their secondary school, and we have their primary school. And it's pretty logical to assume that their high school exit exam would vary randomly across their high school, but also across their primary schools, right? And so that's what we want to know. Can we model this? Can we model the extent to which those scores vary, not just between their secondary schools, but also between their primary schools? All right. And this is a non-nested model because the secondary schools, there's fewer of them, and they draw students from multiple primary schools, right? So one secondary school might get students from 3 different primary schools. Okay. So this is how we do this. The syntax is actually just the same as we've been doing, because we've always been assuming that the data are, that the IDs are explicit. Okay. As long as the IDs are explicit, then nested and non-nested syntax is going to be the same. But if the IDs are not explicit, then it's not. Okay, that's what we just went over. But in this case, now we are estimating a cross-classified random effect model that has 2 different sources of variance, their secondary school and their primary school, as predictors of their achievement. Okay, so the achievement is the outcome. We're estimating what's the average achievement, and how does that average achievement vary across their primary schools versus their secondary schools. Okay, so that's it. And then we can look at the estimates here, we see the average score was about 6.35, and that randomly varied across primary schools with a standard deviation of 0.41, and randomly varied across secondary schools with a standard deviation of 0.26. Okay, so we actually are saying in this case, imagine it's a high school exit exam or whatever, are randomly varying more, there's more variance related to their primary school than their secondary school. Okay, and that actually makes a fair amount of sense to me. The other thing that is cut off on my slides, but you will be able to see if you run this, is there are 50 primary schools, and I think there's 30 or something secondary schools. Okay, so you can see that these levels are not like, they're not the same. There's not 50 primary and 50 secondary or whatever. Okay, when we're looking at the random effects now, so there's lots of different ways we could do this, right? But I'm just pulling the random effects, and then I'm using this str function that says, give me the structure of this thing. And it's a list with two different things. We have the estimates from the primary school and the estimates from the secondary school. If we're thinking about how we would make predictions for an individual student, right? We would take the overall average, and then we would add in the random effect for their primary school and add in the random effect for their secondary school. Okay, so even though we've always thought of schools as sort of this unit that things are randomly varying across, in this case, we've sort of split that and said we have primary schools and secondary schools, and we're going to add both of those random effects for an individual student. Okay, so it's a little bit complicated because one student, you might have two students who have the same secondary school, but they have different primary schools, and the random effects that you're going to add in from those are going to be different. So even though you have two students from the same secondary school, you probably have different estimates for them. Okay, does that make sense? Questions on that? Okay, here's what the image looks like from that model. And you can see there's a lot of gray here, right? It's fuzzy. And then these are, I think, the primary schools, could be secondary schools, I'm not sure. But you can see even those vary because of the numbers vary, the size of those. Okay, here's a zoomed in version. So first 50, you can see you just have a bunch of these little gray squares, because it's not like there's a real pattern here between primary schools and secondary schools. They're just cross-classified, and they're not purely cross-classified either. You can have complete crossing where every level is associated with every other level, right? That's a purely like a complete cross design. This would be like a partially cross design. So it's not like students who are in primary school 1 ended up in secondary school 1, right? So that happens every time. And secondary school 1, say, draws from primary school 1, 2, 3, right? And then secondary school 2 draws from 3, 4, 5, 6, right? So let's just say that's the pattern. If it was a completely cross design, which is impossible in this case, but secondary school 1 would have students from primary schools 1, 2, 3, 4, 5, 6, and secondary school 2 would draw students from 1, 2, 3, 4, 5, 6, right? So every secondary school would draw from every primary school. That would be a complete cross design. And that happens sometimes with experimental designs, but it doesn't usually happen with this kind of longitudinal stuff. Okay, we can extend this same sort of thing, though, also to think of this in terms of multiple membership. Okay, so a student went to a primary school and a secondary school, and so they were a member of both of those schools. So rather than thinking of these things as two independent random effects, we can think of them as one random effect that comes from having multiple membership. Okay, and this is really common in lots of cases. So I've seen it in nursing studies where patients are have multiple memberships with multiple nurses, right? So they are cared for by multiple nurses. And similarly within schools, students very regularly have multiple teachers. Even within a year, if you think of like secondary schools, right? You could have a student who has 6 class periods and has 6 different teachers. So therefore their, achievement is in this multiple membership design. So you could estimate those as all different random effects, or you could think of it as a teacher random effect that has this multiple membership structure. Okay, that's what we're doing here. BRMS actually includes a way to directly estimate multiple membership designs. And this is like amazing to me because I tried to fit multiple membership designs like 7-8 years ago and it was really hard and I was never successful. BRMS now makes it super easy. So in this case, we're going to now estimate, we're going to use a multiple membership design analysis to estimate a single random effect for schools, but we're going to say that it is sort of weighted by this multiple membership design, primary and secondary. Okay? And this is all we have to do. And it's like, I know probably most of you have not struggled with this like I have, so this is not that big of a deal, but to me it was like, oh my God, like I can't believe that's all you have to do. In the random effect part here, you just say MM to stand for multiple membership, and then you state the different components, okay? And you could have 1 or 2 or 3 or 15 things that you add in there, and it will say, okay, these are all the multiple membership parts. By default, as we've done here, it will assign equal weighting to each of those. So it will assume 50% of the random effect should be drawn from the primary school and 50% from the secondary school, okay? And then we estimate the model like that. I have taken a screenshot of the output here because for some reason I couldn't get it to render when I was running my slides, but it ran for me fine outside of knitting, okay? So then this ends up looking like this, all right? And so here's our population, intercept, right? 6.33. So students scored on average on this test 6.33. But now we're saying they randomly varied across schools with a standard deviation of 0.53. Okay, and that school has this weighted multiple membership structure. All right, so that's the primary difference here. However, very regularly, we don't want to weight these things totally equally, because what if a student was in their primary school, and like in this case, this probably doesn't make a lot of sense, but I didn't want to switch data sets and everything again. But you could imagine, right, in a more typical longitudinal sort of design, a student is a member of 2 or 3 schools, and they spent 80% of their time in one school, 15% of their time in a different school, and only 5% of their time in the third school. If that's the case, you don't want to weight them all equally and say, here's 3 schools that they were a member of. You'd want to say 80% of their time was in this school, 15 was in this school, or 80. I think my math is wrong there. Whatever. You know what I'm saying, right? You want to spread out that those proportions and say most of the variance should come from this one school, not these other ones. Okay? So what I'm going to do is just pretend that we have a primary school and a secondary school where we have proportion of the time they spent in each of those schools. Okay? So I'm going to create some new columns just randomly. And so this is like a fair amount of code, but basically I'm creating random normal for 1,000 because that's how many rows there are. And then I'm just computing the sum of those 2 random random values and then dividing by them. Okay. So then we end up like this. So this student in this case, we're saying spent 37% of their time in this school and 63% of their time in this school. This student was about 50-50. This student was 27% of their time in this school and 73% of their time in this school. Okay, so this is what these weighting variables would look like. And you would do this based on time spent in that school or maybe some other thing. This could also be like if you had a research design where it was related to like intensity of the intervention or whatever. Okay. And then what we do to include those weights in the multiple membership is we have MN, put our two things here. And again, that could be many. And then we just add an additional argument, weights, which is an argument to MM. Okay, weights, and then we just use cbind, and then we list those weights in there. Okay, and then we end up here. This is small because this ended up really long, but our estimates all end up looking exactly the same, but now we've accounted for the time that they've spent in those different schools. Okay, so I'm going to stop there because we're out of time anyway. But there are additional slides there on estimating a one parameter logistic IRT model if you're interested. And like I said, there's a bunch of stuff that we didn't cover, but hopefully at least today gave you a window into some more advanced things and more sort of areas of exploration you could think of going to. Okay. Any questions or anything anybody wants to check in on before we sign off?
I have a question. In say you're like using these like kind of multiple membership models and you're trying to evaluate kind of the treatment effect of something that's like, let's say at the teacher level and a student, you know, has multiple teachers because they're in a secondary setting. When you're like comparing kind of the descriptive information of students in each of those conditions, like would you use like the just like the students or like the, yeah, I'm just trying to like think about how I think about the sample. Is it at the student level or is it at the student teacher observation level?
Yeah, so I guess it depends on what it is that you would want to be looking at specifically there. Like if you're like, if you're trying to look at more like inferential statistics, then you would probably be pulling things from your model versus like if you're just wanting to look at them descriptively, then you would just use your data sort of thing. Does that make sense? Sort of?
Yeah.
But yeah, I mean, all of this stuff is really complicated. And this was just a really quick sort of more focused on like exposure versus like really deep understanding of it. But like I said, I've spent a lot of time with this kind of stuff, so I can give you more resources if this is something you're interested in.
Okay, thank you.
Okay, so final projects are due Wednesday at midnight. If by any chance you can get them to me earlier, then I will give you feedback earlier, and I would really appreciate that because then I can make sure that I am not killing myself to get final grades in. But if not, that's fine too. Just make sure it's in by midnight on Wednesday, and otherwise that's it for the term. So thank you all, and I hope you enjoyed the term. I really enjoyed teaching it and enjoyed sort of getting to know most of you. It's kind of hard through Zoom, but it's still fun.